Hello, this will be a demonstration of proposition 6 from book 5 of Euclid's Elements, which says that if two magnitudes be equal multiples of two other magnitudes, and any magnitude subtracted be equal multiples of the same, then the remaining magnitudes are either equal to or equal multiples of the same. What that's going to look like is we're going to have two magnitudes E and F, and of them we're going to have equal multiples A, B, and C, D. And we're also going to have parts of A, B, and C, D respectively also be equal multiples of A, E, and F respectively. So we're also going to have that AG and CH, which are parts of A, B, and C, D, are equal multiples of E and F as well. And what we're going to prove is that either GB and HD are equal to E and F respectively, or GB and HD are equal multiples of E and F. Now GB is either equal to E or it is not equal to E, so let's begin with the case where GB is equal to E. If GB is equal to E, then we're going to make we're going to make the magnitude CK off of CD such that it's equal to F. Now, AG and CH are equal multiples of E and F respectively, right? That was given to us up here. And we have GB equal to E and KC equal to F. And Euclid here takes GB and KC also as equal multiples of E and F. He has to in order to use proposition 5.2. But it is, a little bit strange considering GB is equal to E, and so calling GB an equal multiple of E. It's a little weird, but it's fine. It still works. So AG and CH are equal multiples of E and F, and we have GB equal to E and KC also equal to F. We know that GB and KC are equal to F by virtue of our first step, which means that by proposition 5.2, right, that's the one if you have a first magnitude the same multiple of a second, that a third is of a fourth, and also a fifth be another multiple of a second, that a sixth is of the fourth, then the first plus the fifth is the same multiple of the second, that the third plus the sixth are of the fourth, which means that AB and KH are also going to be equal multiples of E and F, right? AB is AG plus GB, and KH is CH plus KC. So AB and KH are going to be equal multiples of E and F. Now, we were also given that AB and CD are equal multiples of E and F, right? We were given that right there, which means then that CD and KH are both the same multiple of F, that AB is of E. So you can say property of magnitudes that KH and CD are equal multiples of F, which means that that KH has to be equal to CD. That's the only way that works out. If you have two magnitudes that are equal multiples of the same third magnitude, then they're just going to be equal to each other, right? That makes sense. So KH is going to be equal to CD, which means then if we subtract CH from both, we get that KC is equal to HD. That's common notion 3, which I wrote as common notion 2 over here. My bad. So KC is equal to HD by virtue of common notion 3. But we had made KC such that it is equal to F. That was our first step, which means that we have two magnitudes, HD and F, which are equal to the same thing, KC, which means by common notion 1, they are equal to each other. And so we can say that HD is equal to F, so that now we have GB and HD equal to E and F respectively. Now, that was our first case, but the other case is where GB is not equal to E. Well, if GB isn't equal to E, it has to be some multiple of E. And you can think of it like this. If you have, let me think. Yeah, so let's say you have 3 and you take some multiple of it, 12, right? 12 is a multiple of 3, so it's 3 times 4. And you subtract from 12 another multiple of 3, let's say 9. So, or let's do 6 here actually. You subtract 6 from 12, right? Because, and we know that 6 is also a multiple of 3. And so the remaining bit, well, 12 minus 6 is 6. 6 is a multiple of 3. So that's basically what we got going on here. So either GB is equal to or unequal to E, and if it's unequal, it has to be some multiple of E. Now Euclid doesn't go through the all the steps, but I'm going to. It's a little bit fun. So if we have GB being some multiple of E, we're going to make CK the same multiple of F that GB is of E. We follow, very similar steps. We note that AG and CH are equal multiples of E and F respectively. We were given that. And we have GB and KC equal multiples of E and F as well, which means that by proposition 5(2), again, if we add AG and GB, it's going to be the same multiple of E that CH plus KC is going to be of F. So we're going to have AB and KC equal multiples of E and F respectively. Now we were given that AB and CD are also equal multiples of E and F, which means then by a property of magnitudes, KH and CD are equal multiples of the same F, which means that KC has to be equal to CD, which means that if we subtract CH from both, KH minus CH is going to be KC, and CD minus CH is going to be HD. So by combination 3, we can say that KC is equal to HD. But we had made KC the same multiple of F that GB is of E, which means that HD is the same multiple of F that GB is of E. And this is what we set out to prove, which means we are done with the proposition, right? Either GB and HD are equal to E and F respectively, or GB and HD are equal multiples of E and F respectively. And we have just proven that either one of those must be the case, which means we are done with the proposition, therefore, etc., Q, E, D. Now again, we can put this into more understandable algebraic terms. What that would look like is if you have some magnitudes A and B like that, and we take some equal multiples of them, that's going to look like MA and MB. Right, so we just multiply these by A, or multiply these by M. And if we have M being greater than some N, and we also take NA and NB, right? So M is, or N is going to be a part of M. That's what the language of part subtracted corresponds to in proposition 5(6). So if we have equal multiples AB, if we have equal multiples of A and B be taken, MA and MB, and we have parts of these equal multiples taken or subtracted that are also equal multiples, so it would look like taking NA and NB away from MA and MB. Then we're also going to have the remainders, which, so if we subtract MA minus NA, that's going to be M minus NA. And if we subtract NB from NB, that's going to be M minus NB. What we've proven is that these remainders here, M minus NA and M minus NB, are also equal multiples of A and B, right? Namely that they are M minus N. They are multiples of A and B. Okay. Now, the two cases that correspond to this are that whether M minus N equals 1, or if M minus N is, it's greater than 1. Now, M minus N can't be less than 1 because we have that M is greater than N, so, it can't be less than 1. So these are only cases where where M minus N equals 1, which is our first case where GB is equal to E, or that M minus N is greater than 1, and that corresponds to GB being some multiple of E. So that's all I have to say about this proposition. It's, it's fairly nice. It corresponds to, what does it correspond to? It corresponds to 5(2), I believe. So that's all I got to say about this proposition. So I'm going to end the video here and move on to 5(7).